Yeah. Can you hear something? Right. You can hear something or? Hi the world. We're live streaming. Yeah. Maybe you can hear the speakers. Maybe if you go outside, I don't know. I'll go outside later.
Okay. It's loud.
Yeah.
But when they're silent, I think it's going to be loud.
Yeah. Good. So we're ready to go. Sorry for the delay. So our first speaker, Ines. Thank you. Next, yes.
Okay. So hello everyone. My name is Ines. I'm a third year PhD student at Geops in Orsay, not too far from here. And I'm going to present you the pipeline that we've developed for using image processing for precise geometry determination. So this is the work that's been done in collaboration with Airbus Defence and Space in Toulouse. So a little bit of context first. We've developed this for my PhD, which is a photometric study of Jupiter's icy moons. So the idea is that we have a collection of images taken with the Voyager and New Horizons spacecraft, and we want to be looking at the surface of the icy moons from different vantage points and with different illuminations, so we can characterize their response and infer physical properties on the surfaces. So the problem we have is, how do we get reliable geometric information from those remote sensing images? Because what we want is the reflectance versus the geometry of observation, so the incident, emission, and phase angles. So what resources do we have? We have access to the PDS archive, where we have all the images from past NASA missions. And we also have SPICE kernels, which are files containing information about the spacecraft, the instruments, and also the context in which the images were taken. So for projecting each of these pixels in this image, we need three major things, which are the spacecraft position, the spacecraft orientation, and the target's ephemeris. So first things first, before getting into any of that, we corrected for the distortion, which is really important in the Voyager data set. So for example, this is a raw image taken with the narrow angle camera in Voyager 1. And this is the same image after correction. So we developed a tool for that. And then the heart of the pipeline is really the metadata correction, because as I said, we need three major informations, but this information contained in the kernels may be flawed. So we need to look at it. The first thing is, I'm going to detail the spacecraft part of the pipeline. So for example, the pointing error. So to look at it, we did simulations using Surrender, which is a tool developed by Airbus Defence and Space, to simulate images in the same conditions using the SPICE metadata. The idea being that if you have the correct metadata, you should be able to simulate an image that's exactly the same as the real one. You can see here that it's not the case. You cannot see the graduation, but there's 100 pixels difference approximately between the two, and it's not in this right spot. Another way to look at it is, if you project the shape of your target into the image frame, you obtain the red circle rather than the blue one, which means that you think you're looking along the red vector when you're actually looking along the blue vector. So to correct for that, we simulated images in every situation, and then we developed a tool of image registration to compute the offset and then pointing correction in 3D. We also looked at the spacecraft position, and more particularly the distance, because as you can see here, so in red you have the limb, which is the edge of the moon, of Europa here, and you can see that the moon is actually extending beyond the limb, which means that it's closer than we think it is. So to correct for that, we've developed another tool where we did simulations between 95 and 105% of the distance, and computed the likeness to the real image and selected the one for which the likeness was the best one. So this is the entire pipeline that we use on our images. Once this is done, you can calibrate your images and project them safely in the coordinate system so you can get the geometry that you want. We used it on Voyager, on New Horizons, and on Galileo images, but this algorithm should be applicable to really any kind of image data set with a similar resolution. So that's it for me, and now I'll take your questions.
I think I can speak now. So similar tool for ISS on Cassini data. I think it's from DLR, so it's not probably closed source. So are you planning to make it open so that not everybody has to invent this?
Yeah. For now, I'm finishing my PhD, so it's not the immediate plan. But and we're working with Airbus Defense and Space, so we have to. It's not that easy to make it open. But we can talk about it in the coming months to when I finish everything to make it open on GitHub. It's on MATLAB, so you have to be on MATLAB. Yeah.
And then as a follow-up, I guess you do that on. On single images, on a subset images.
On single images.
More like manually, right?
Not manually. The whole point was to have something that's automated. So it's completely autonomous, and you can replace any of these boxes with another algorithm, and you can replace the simulator with something else, but you can completely automate it with no problem. You don't have to select anything by hand.
So when you, at the end, there could be a new kernel, right?
Yeah, that's the first thing I want to do before making the software open. I want to generate new kernels with high data. Yeah, because I haven't had time to do it yet because I haven't seen trouble with the functions. But I've been talking last year with people from the remote that have worked a lot on the Voyager data set, and I'm planning on reaching out to them again to find a way to generate those kernels and make them open. Yeah, that's the first thing I want to do.
So you don't only look at the limb, but also at the structure inside the image, right?
It's the image registration part is based on intensity, so it's an optimization loop on intensity-based registration.
Okay, I mean, if this was not the case, in principle, there could be the same efficiency either caused by wrong spacecraft position or wrong spacecraft magnitude. But if you really simulate the image, you can in principle distinguish between the two. But I'm not sure if this is, if you really have a unique solution, or if it's somewhat uncertain. Maybe you can correct an image either by moving the spacecraft position or by changing the spacecraft magnitude. Can you really distinguish these effects?
We tried to, I actually developed another tool because I wanted to not just correct for the distance, but correct the position of the spacecraft. And we found that the field of view was too narrow to distinguish between translation and between rotation. So we couldn't, we didn't have satisfying results to have a clear determination. So what we did was we just corrected for the depthness, for the distance, and then we corrected it as an attitude issue with the spacecraft, and then we couldn't really distinguish between all the different positions.
Background of this is when the Cesiumjs camera team on Rosetta did their shape modeling, as a byproduct, we estimated new spacecraft positions. And they gave these to us saying we would improve the position curve. But it turned out the spacecraft position by dynamics is very accurate because they also do modeling and everything. And the museums even assume that the pointing they get is correct 100%, which it is not.
Yeah.
So the spacecraft position corrections they gave us are really pointing corrections.
Yeah.
But this is not.
It's not an easy thing to distinguish between. Yeah. You have, like I said, even what the corrections that we did, I didn't develop this, but we've also looked at the moon's attitude. So basically, once we did the correction for the spacecraft pointing in 2D, we corrected, because we can't have this angle when we do what I just told you about. So we looked at an optical floor. So basically, that's a local correlation for each pixel. So you get something that looks like this. This is simulated, but that's the idea. You get a motion that you can project in 3D. And we decided to correct for that as the moon's attitude. But it could also be that the spacecraft is wrong in this angle. So you cannot, from what I found, you cannot distinguish between the two. So you have to make a choice, and to be clear what the choice that you make so people can use your data. But there's really no unilateral way to decide which correction is better.
Yes, I'm sorry we don't have time for another question. So thank you, Ines. Jakub, it's your time.
So the one. The one?
Yes, perfect.
Okay.
I have just 5 slides, so I think we can gain a little bit of time. I'm Jakub, I'm from Poland, from Space Research Center in Wrocław. We have a small group led by Daniel Mesh, and we focus mostly on volcanic and tectonic processes, I would say, with some thermal inertia calculations too. But here in this talk, we'll fully focus on volcanic processes on Mars. And doesn't work? Okay. Just a little bit slower. Okay, no problem. So on Mars, we have 2 major volcanic provinces. One is the keyboard. Okay.
If you want to do next.
No, just wanted to laser pointer.
It's here.
Okay. Thank you. So one major volcanic province is Elysium, and the largest one is Tharsis volcanic province. In Tharsis volcanic province, we have about 600 large and small volcanoes. So tomorrow we will have another talk about these small volcanoes if you are interested with them. But today I will talk about the largest volcanoes. We have 12 major volcanic centers in Tharsis. And what is interesting, that all this volcanism is generally very active until very late Amazonian. So we were interested why this is so active and where we could find the most active volcanism there. So we did some geomorphological study. Let's say we measured volumes of these volcanoes using molar data, and we did also dating. We dated summit calderas of these volcanoes. And the results of this are quite stunning. We found a correlation between volcano age, the youngest activity in the calderas of the volcanoes, and the volumes of them. So this is the age, these are the volumes, and you have quite a distinct correlation between them. So this is relatively robust, and now interpretation is of course more difficult. And one way how this could be interpreted is that there was a beginning of volcanism early in the history of Mars, somewhere in Noachian, and then smaller volcanoes grew just for a while, just for a short period of time. I mean, not a while, of course, in the context of geological history, but larger volcanoes grew, and they became very large. And potentially, some of them could be even active today, not active, but dormant, and could be activated in the future, potentially. And that thing was quite robust. This is a thing which is, of course, more speculative, but we were able to calculate magma flux based on that information, which was on the previous slide. And on the poster, of course, I can show you details. But the most important thing is that you have probably still long-term magma flux, eruptive magma flux on the surface. And this is how this would look like. So you had back in the history, Noachian, Hesperian, you had lots of magmatic chambers. Then very little of them survived until today, but only below this large volcanoes like Olympus Mons, potentially Arse Mons, but nothing under smaller volcanoes. So this would respond to a question where we could expect potential future volcanism on Mars. So that's it for now. I invite you to discuss more at the poster session. Sorry, could you repeat, please?
Yeah, you mentioned in this graph other volcanoes. How did you constrain those ones?
Which one?
The black ones.
Okay. So these are smaller volcanoes. I mean, not small. These are separate volcanic centers, but like this Uranus Mons, like Tharsis Tolus. So these are also constrained by the age and by the volume.
All of them.
So 12 largest, and then they have, of course, their parasitic cones, etc. But there are 12 largest volcanic centers in Tharsis. We did map, yes. Mm-hmm. We did map also this small. Mm-hmm.
You still have time for questions?
Thank you.
Thank you. Jakub?
Hello, my name is Maxim. I'm from University College London Muller Space Science Laboratory, and I'm very new in planetary science. My background mostly remote sensing, and so my short presentation is about application of CASP-GO for retrieval of 3D information for candidate landing sites on the moon. And so the thing is that they expect new wave of moon exploration, and due to this, they are exploring some possibilities of obtaining 3D models for landing candidates. The problem is that currently digital elevation models for moon have maximum 20 meters spatial resolution. But using our software, which names CASP-GO, which is for Gauge optimized AMI stereo pipeline, we can obtain DEM or DTM with about 1 meter resolution. For this, we will use lunar reconnaissance orbiter camera, LROCNAC, and we are planning to use lunar orbiter laser altimeter, LOLA, and Chinese chunk-E DTMs to fill the possible gaps in our retrieval. And so this is a representation of data we collected so far. And is it a laser? Okay, let's know. And here you can see the bright square is the LOLA plus Selene DTM. The dark square is the chunk-E DTM, which actually perfectly fit to each other. This means that we can easily use this data to fill the gaps. And also we can see red outlines, which shows coverage of LROCNAC stereo pairs, which currently available, and we will see that they are not perfectly cover all the surface of a crater. I forgot to say that very important thing, sir, that craters were interested in names Aristarchus and Copernicus, and there are a few reasons why we are particularly interested in these craters: geological, possible availability of water, and proximity of polar landing sites. And coming back to this, let's explain. And the other possible source of the data, which is the lunar orbiter image, which also available as a stereo pairs. And lunar orbiter was a mission of NASA to prepare, let's say, in preparation of Apollo program. These images were done in 60s, but they have very high resolution, like some sites, like this one, in 2 meters spatial resolution, which potentially allows us to use this in 3D retrieval. So other crater is Aristarchus crater, which is relatively younger than Copernicus crater. And in this case, this crater fully covered by LROCNAC stereo pairs. This means that in this case, we don't need additional, potentially, we don't need additional data for 3D restoration. And so far that's it. We prepared the data and we have our in-house software. And any questions, please? Oh.
Hi. Do you achieve these resolutions just in one areas or also, especially in the south?
It just depends on availability of stereo pairs, because in general our software allows to produce high resolution. And then it depends on the resolution of stereo pairs. And the resolution of stereo pairs, yes, it can be, it depends on equatorial area or polar area. Yeah. Yes, exactly. All these will definitely affect the final result.
Other questions? Okay, so we can thank Maxim.
Next one. Just give me a second.
Okay, thank you. Hi, my name is Marta, and I'm from this Polish group. And I would like to talk to you about some thermal mapping of the Martian surface. And we are especially interested in thermal inertia, and it may gives us the information about surface composition in addition to visible images analysis. So the idea is very simple. We need only albedo and temperature difference to calculate apparent thermal inertia, because we cannot measure it directly, of course. But then we need something more, atmosphere and topography correction, which we included in our calculations. So it makes things more complicated, but still I believe that using our approach, every of you could make its own apparent thermal inertia map. So the data we are using, you can see here, and depending on which approach we are using, if we are using daily temperature difference, we call it apparent thermal inertia, then we need daytime and nighttime images. We can also use the other approach, which is called differential apparent thermal inertia. Then we use 2 daytime images. Sometimes it's easier, and because we have bigger data set to use. Okay, and the example of apparent thermal inertia. So we choose a very challenging place, Valles Marineris, with very steep slopes, as you know, because we wanted to test how our approach will work for this extremely steep slopes. Because so far, existing thermal models were using rather for flat areas. For sloping areas, it was really challenging to use. So at the end, we got satisfactory results. By analyzing in visible images our results, we think we are going in a good direction in our approach. And here is the example of the second approach, which is actually the same as the previous one, but we can use 2 daytime images. Sometimes it's easier to find them. This is the example of Olympus Mons caldera, and we found here some interesting area which may represent hard rocks, but maybe going further, some internal heat in there, maybe going even farther, future caldera. And at the end, thanks to collaboration with PI of PFS instrument, we got access to surface temperature data from over 9 Martian years, so 11 Earth years, so very big data sets, and we can analyze them now and make some conclusion. We made some averaged map as well as seasonal maps, and we calculated also thermal inertia. And what we have noticed that ice caps are very well visible in these maps. So we hope now to track, based on this data, ice cap changes over seasons. Even we think that it will be possible, based on thermal inertia information, to distinguish water ice from carbon dioxide ice. And in the future, we also hope to use ACS data. These are also surface temperature data from ongoing mission ExoMars. So in short, that would be all.
Any questions?
So how this work relates with for example, the Robin Ferguson
Oh, yeah.
work of 2006.
Oh, I even know it by heart, I must say. So the good thing is that we've got almost perfect agreement in flat areas. So I think that it's kind of validation of our method. But I know that because she was, I mean, the aim of her work was to make a global map. So she somehow do not include really topography in her calculations. But anyway, she's writing that the slopes over 20 degrees are very questionable in terms of thermal inertia values. And we think that thanks to our correction, it works better for these sloping areas. Yeah. Mm-hmm.
Any other question?
Okay.
So thank you.
Hello, my name is Chiara. I'm from Geomorphological, Paris Sud University. So today I'm talking about a Cesiumjs application for planetary data visualization. This Cesiumjs, what is Cesiumjs? Cesiumjs is an open source JavaScript library working well with 3D visualization. Thanks to a Europlanet funding, we have worked on extending Cesiumjs for planetary data, because Cesiumjs has a lot of GIS software very tied to Earth data. So our prototype is linked between the Cesiumjs demo. So if you look for it, you can just ask for the planetary surface GIS experiment on Cesium, and you can find the page. What we have added a better generalization for planetary data, and we have added some connection to the VO services. So the prototype can display, can connect to VO servers and ask for features available via the EPN TAP protocol. And it can visualize the VO features, the VO feature attributes. We have done some new work on that, starting from, we have experimented some topography using exoplanet, simulated exoplanet data. This is a work done by Landau, Schmidt, and Lovejoy 2019. So you can access, it's visible that? Yeah, okay. You can access the Cesiumjs visualization interface via this, this address. We have experimented a bit, and then we have found a way to publish the planetary topography. Well, for now, you can have Mars, Mercury. I have some problem with the moon, but maybe I can do that. The interesting thing is that the format for the topography is an open format described at this address, and we have found an open source way to translate the DTM raster in this open format. So we have used the Cesium terrain builder from the Geodata organization on GitHub. What we want to do next? Well, we hope to install the prototype at the IPSL, the Pierre-Simon Laplace Institute, because IPSL is the organization with which we will participate to the new Europlanet call. We hope to integrate some data, some atmosphere data, and hope that the next Europlanet bid will be successful. And thanks if you have any questions. Nope.
You mentioned a connection to the video. Does that mean that you implemented the same problem inside?
The connection is, well, we have a widget that can query an EPN TAP server with a configuration file in which we can add via a JSON file, we can add the server we want to add to our interface.
You have a client?
Nope. For now, okay, this is web. So what we do now is that we ask for JSON format in output from the EPN TAP server, and then we parse the JSON format and we display the feature there. My hope is that just to put a point on the surface. But if a polygon is available, we can display a polygon.
So yeah, going the similar direction. So you kind of implemented a JavaScript, I guess, client for view.
Yep.
Okay.
Well, it's a JSON parser. Almost.
Oh,
that's easy.
Well, yeah. So still you have to do a SQL request.
Yes. Yes.
Well, even if it's hard coded, but you have some structure that.
Yep. Yep.
Okay, that's cool. Because I have something that I've done in Python, and maybe we should find.
I will be happy to
have something like either web available or. Then the other thing that I want to ask is these modifications that you've done to Cesium. Is it being committed to Cesium repository straight, or do you have a fork? Or
we have a fork on the EPN VESPA organization, because I don't think the code is ready for a pull request, because there are a lot, well, people from Cesium have hidden very well dependencies from WGS84. So sometimes we needed to invent some trick to forget. We had to redefine the WGS84. So I think that the code is not clean for a pull request. It's usable. For example, for the WMS, we changed in a generic way the code. But for example, for topography and for JSON display, we had some problem because somewhere we can't. I think that they defined the WGS. They put the WGS84 very deep in the code, and when you zoom a lot or you dezoom a lot, the objects disappear, because I think in the first DOM they define something connected with the WGS84. So I don't think it's good. It's ready for a pull request. But the code is there, and everybody is welcome to contribute, because I think that this library is a very good library, and it's GIS ready. So if you need an interface for Planetary with GIS analysis, you can use it, but WGS84 is very deep inside, so difficult to. Okay.
So if you do based on WGS, then you probably don't have a nice view of the whole. Can you do measurements of the whole?
Yes. Okay, now wait. For measurements, my problem is that in Cesium.js, you have the WGS84 everywhere, okay? So for some functions, some features, we could find the dependency, and we generalize it. So we define ellipsoid for Mars, Venus, Mercury, and for all the you can see here, but we define ellipsoids for all standard IAU ellipsoids for all the planetary bodies. But somewhere they did something I can't understand. So for measurement, I can use the true ellipsoids. For visualization, somewhere there is still WGS84 somewhere, and I don't know where. I think that in the WebGL code they put something, because, as I said, it's for example, if you have a GeoJSON with elevation information, sometimes the GeoJSON for Jupiter, the GeoJSON is based on is under the surface, and for Mercury is too much higher. So there are some small problems, and we didn't find the way to trace them. But for measures, it's working.
Quick question. Can you plug non-implemented services, aka WCS?
Sorry?
Can you plug WCS endpoints into Cesium.js?
Web coverage service? So not yet. Okay. Well, the background maps are WMS. So I can do with Cesium. Cesium is used for WMS and WFS. So you have, by default, you have WMS, WFS. WCS, no, is not implemented. But, well, I like the idea to have a mixed system. So if I can use WCS and VO visualization, I will use both. So this was the idea, to have widget, independent widget that I can choose and put in there if I need. But no money, no more money for now.
Time for another question.
Look deep into the code because we always hide hard content of this WTS 84 things. I had the same problem.
Okay, yeah.
Okay. Non, c'est pas. Surtout non. J'achète. T'es prêt?
Non, c'est mon téléphone.
Ah, c'est ton téléphone.
Good afternoon. So I will focus my talk on the detection and mapping of these supposed tsunami deposits in the northern hemisphere of planet Mars. We did that work together with Antoine Séjourné and Emeline Garret. She's a Master 1 student. And we have an online paper since a few days in GGR Planet about it. And 2 years ago, we did also a paper about that idea. So let me remind you that the idea that there was an Earth and ocean on planet Mars, it's still a controversial hypothesis. And in the last few decades, there was many papers about the detection of paleo shorelines. And there was some study by Tim Parker, Steve Clifford, and Gaten Zibelman, who detected some paleo shoreline. This one, for example, the white line corresponds, that's the polar projection, that's the polar cape on the equator around. That's the crater plant here on the Tharsis region. And the white line corresponds to the contact 2. That's the Deuteronilus paleo shoreline detected by these geologists many years ago using some morphological features like these linear features here, together with the use of the molar laser detection of some constant elevation here over a distance of a few hundred kilometers, which would correspond, according to these geologists, to some paleo shoreline. And that line would correspond to that contact 1, which corresponds to an elevation of minus 3,600 meters. And the other one is the contact 1, the Arabia paleo shoreline, at an elevation of 1,600 meters. That's the black line here. A few years ago, in 2016 and 2017, independently, 2 international teams detected some low-bait flows in Arabia Terra, that's the area here, which exhibit some low-bait flows of about 10 kilometers wide and 10 meters in thickness, which overlap some pre-existing topographic features, these mesa here, and you can see these low-bait features overlapping these topographic features. And here are again the mesa here with some compressional feature, which clearly indicates some flows coming from the north to the south. And that's true for all that area in Arabia Terra. So we did that work, and we did a publication in 2007, and a few months before the US team did the same observation. The leader was Alexis Rodriguez. And the second observation, a quite interesting one, is for all these low-bait fissures in that area. Here again, the low-bait fissures here, and that's the molar data with individual laser shot here, which indicate the increase of the elevations over a distance of a few 100 kilometer distance, and an elevation of 100 meters, an increase of 100 meters. And that is true for all these low-bait fissures. which correspond to some run-up. And that's a figure which shows what is going on Earth. You have these low-bait fissures produced by some tsunami waves, like in Indonesia or in Japan, for example. And during the propagation of these waves, there is the waves go through the land with an increase of the elevation due to the energetic flows. And between the first and second waves, there is a receding of the waves with some linear erosions. And here, this is an example, typical example in Arabia Terra, showing the low-bait with low-bait fissures with the run-up here, the increase of the elevation, and some linear features. That's the red arrow, linear fissure, which were detected and described as as produced by the backwash of the tsunami. So we tested that hypothesis with Karim Kelfoun from the Clermont-Ferrand University, using a numerical modeling, the red color corresponds to the propagation of the waves from marine impact craters. The best candidate for us is the Lomonosov impact craters, 150 kilometers in diameter. And here is the last step of that propagation, which corresponds to the detection of these low-bait features observed in Arabia Terra. So we decided to do a detailed mapping of these low-bait features in order to better understand the dynamic of these supposed tsunami on Mars. That was a long time ago from the crater counting technique that ocean and these tsunami were produced, were active around 3.5 billion years ago, between 3.5 to 3 billion years ago. And we use for that the TEMIS imagery, the MOLA data, of course, and we did a first overview of this area with the Google Mars software, a very powerful software, online software, and then we did a detailed mapping very carefully with the ArcGIS software, and we use different layers, and we had all these layers with different kind of data from the different image, and the detection was done by hand for all these areas. So here is the global map. That's the polar projection, which shows the yellow line, which is the paleo shoreline, the contact 2, and you can see that the detection of these low-bait deposit that correspond to the red line here, had a quite good correlation between these detection and the paleo shorelines. And there are some interesting observation in Isidis Planitia, so we are working on since the last few weeks. So in the near future, yeah, that's the end. In the near future, we will work on the virtual reality software together with François Costard from Nantes. The idea is to have a complementary approach in order to better understand the configuration and the interaction between the low-bait flows and the backwash, the linear feature observed around these low-bait flows. And that's the end of the talk. And I am ready for the questions and later for the coffee break if you want.
You have 2 minutes.
I just have one question. Was it possible for you to estimate how often such tsunami events occur? Then you could see recording the deposits.
Yeah, well, in fact, it's quite difficult to have easily a record, a dating of these episodes. We did it for the Arabia Terra with the crater counting technique, and we find an age of 3 billion years old. And from the numerical simulation, independently, we did the same method, and we did the crater counting inside the Lomonosov and outside in the ejector, and we find exactly the same age. So the idea with the mapping program is to estimate the age of these supposed tsunami deposits and to see if they have the same age or not. So about your question, if there was some different tsunami, the US team proposed 2 different episodes. And from the French team suggests 1 episode. So we are working together with Alexis Rodriguez about it in order to better define the, it's not so easy because you need to use the criteria counting, so you need a coverage, an important coverage of the unit in order to have a statistical data, enough data from the impact. But it seems that we have maybe some other tsunami, but the larger one anyway would erase and remove all the previous one. So it's quite complex anyway. So but that's the idea. That's the main objective of our mapping.